Good afternoon to the Resonex seminar. We have visitors that join us remotely. Welcome visitors on Zoom. And we are here in the classroom. And as always, I will give a little bit a rundown of what we do. Somebody this might be your first time you visit us. We have the Resonex seminar in the classroom of materials, resource, and sustainability. And we have this also as a seminar for anybody to join us remotely. I will introduce our speaker and who will then give a presentation for 40 minutes. Thereafter, we have the opportunity to discuss the reading prompts, the prompts in the classroom here at our tables. And then we also will have time, those joining remotely, to join the breakout room for that, or you might prefer to just hang out a little bit till we have the final Q&A for about 25 minutes after that breakout. And with that, it is my great pleasure to introduce today a speaker from our own. Dr. Claire Zhang is a professor here in the Micron School of Material Science and Engineering at Boise State University. Dr. Zhang received a bachelor's degree in applied chemistry and a master of science in inorganic chemistry from East China University of Science and Technology, and a PhD in electroanalytical chemistry from the University of Pittsburgh. She conducted postdoctoral work at the Harvard University and at Argonne National Laboratory on lithium-ion and sodium-ion batteries. She joined Boise State University in 2012. Dr. Zhang received many awards, including most recently the prestigious Charles Hatchett Award in 2024. Dr. Zhang is a fellow of the American Ceramic Society and of the Royal Chemistry Society. Please help me welcome Dr. Zhang.
Thanks very much for the invitation and introduction from Professor Muller. And it's great for me to come back to this seminar series again to discuss. So I changed the title a little bit, but the kind of topic is still similar. So in today's talk, I'm going to discuss about why do we need the low-cost and earth-abundant electromaterials for rechargeable batteries, especially for lithium-ion battery and beyond the lithium-ion batteries? Okay. Probably I don't need to do a lot of introduction why we need batteries, because I think you use all the electronics that's powered by batteries, and also the transportation as well as the large-scale energy storage using like renewable energy, right? So you can see, especially for the current leading technology, which is the lithium-ion battery, it dominates the portable electronics market, and it also has a growing market in terms of the automobiles and as well as for like large scale energy storage. And if you're looking at the kind of the large scale energy storage, especially if you want to use the renewable energy, we know like you can only like have the power when sun shines, right? So when it's dark at night, you cannot have any power generated. So the idea is like, but most of the time we might have the peak of the demand, not at the peak of your generation of the renewable energy during daytime, right? So we need to have some means of energy storage, then you can store the energy and then supply when it's needed. So this is why the large scale energy storage is in use, especially for the load leveling for the power grid. So I just attended a kind of a workshop last week, and it's like people from Australia, they are also interested with battery technology. So we have a workshop between US and Australian researchers talking about the need. So they said like especially for this large scale, like a long duration energy storage, the timing is very important. So they said like when you store your energy and when you give out, right? So that also add a lot of requirement for the energy storage system, like how much energy you can store and how fast you can release those energy. So that's related to how you can design your materials. And we also need to have a balance of the kind of your technology for the, especially for batteries, right? You want to have a good performance, but you also want it to be sustainable, right? For example, if you use electric vehicles and you don't want your car to, the battery of your car to die within 5 years, right? You want to use it as long as over 10 years. Then there's also sustainability, and also you need to consider the balance between the performance and sustainability with the kind of cost in mind. And we also see kind of the projection in terms of the global need for the different technologies, for the energy storage in different countries. So you can see the kind of general trend is we're going to have a lot of demand in the futures in terms of the energy storage. And if you're going to go back to look at what is the first demonstration of battery, that goes back to the 1800, when Sir Alexander Volta demonstrates first like a device for the practical electrochemical system, which is called the Volta pile. So the Volta pile is like a constructed with a sandwich of layer of zinc metal and also tarnished silver. So that's your two electrode, and that is connected by the paper soaked in salt water, and they can demonstrate it can provide the electricity. So this is the first demonstration of the batteries. And if we're going to look at the current technology of rechargeable batteries, like we said, the lithium ion is still the leading technology. And in our field, we also say the lithium metal is a holy grail of the battery technology, because you can see like it has a high theoretical energy density, both in volume and in weight. But there's also a lot of challenges in realized lithium metal-based batteries, such as lithium sulfur or the solid state batteries, because of the reactivity of lithium. So there's a lot of like safety concerns related with this technology. So there's a lot of our research and development is going on to try to realize this technology. And so if we're going to look at what is the most commercially successful, which is the lithium-ion battery. So a few years ago, the pioneer in our field, Professor John Goodenough and Stan Whittingham. So Dr. Whittingham is actually in that workshop I just mentioned. And also Dr. Akira Yoshino, those are the three key person that realized the technology of lithium-ion battery. So it starts with Dr. Stan Whittingham. He introduced the idea of intercalation materials. So in his first kind of demonstration of the batteries, he proposed this material, which is called titanium sulfide. So it's a 2D materials, and it has a vacant place. So his idea is you have this intercalation material, you have the vacant place that the lithium ions can go in and out, then that will make the battery rechargeable, right? Before that, most of the time, you only have the primary battery, meaning that you can use it for once, but you cannot use it for multiple times. And then at that time, he has this titanium disulfide. It's very, like it has very good cycling stability, and it's also very fast. But the kind of limit is it can only provide 2 volt in terms of the voltage of the batteries. And then the Professor John Goodenough, who passed away 2 years ago in his 100 years birth, after his 100 years birthday. And that's a pity for the field to lose him. And he shows that you can develop a oxide-based intercalation material, which in his case is a lithium cobalt oxide. And by changing the transition metal and also make it oxide, you can increase the voltage from a 2 volt to 4 volt. So this is dramatically increase the energy of the battery, because the energy is the product of the voltage and the current, right? So if you increase your voltage, you double your energy density too. And then at that time, they're still using the metal as the anode materials. But I think at that time, there's a few companies that they are trying to commercialize the technology, but there's a kind of fire accident at that time. So eventually the company was not successful and get bankrupt because of this safety issue of the metals, because lithium metal is very reactive and tends to form the dendrite. So if you have the dendrite penetrate through your separator, which is a physical barrier between your anode and cathode, then they can cause a short circuiting and lead to the thermal runaways. So then I think with effort in the Japanese group and Asahi Kaizen, they kind of developed this carbon-based materials as anode. And this is kind of the start of this the start of the commercialized lithium-ion batteries, and that's done by Sony in the 1991. Okay, so if you're going to look at how a lithium-ion battery to work, during discharge, you will have these lithium ions moving from the anode or negative electrode. So negative electrode means the potential is lower, and positive electrode is potential is higher. And but oftentimes you will also see they use anode or cathode as a term, and that only means during discharge, because the anode means oxidation and cathode means reduction. And in this case, during discharge, you have the lithium ions moving from the negative electrode side through ion conducting and electron impeding, oftentimes non-aqueous electrolyte to the cathode side. At the same time, the electron will travel externally to meet at the cathode side to satisfy the electron neutrality, and at the same time provide the electricity, and vice versa, right? So this is discharge, and then you have charge. So this is how a lithium-ion battery works. And if you zoom in to look at the battery system, actually it's not as simple, because you need to, usually you make your electrode into a composite electrode, mean that you have your active materials, and you need to use the polymer binders to bind them together, and you also will have carbon black to increase the electronic conductivity. And then you also have the interface between your electrode and the electrolyte. So I'm an electrochemist by training. So when we learn any electrochemical cell, you say the electrochemical cell is a collection of interfaces. That's no exception for the batteries too, meaning that in the battery you have multiple interfaces that might affect the overall performance, especially the kinetics of your cells. So you need to, if you design a new battery system, those are the things that you need to take into consideration. Okay, in terms of in how to design materials, and if you want to maximize your output voltage, you need to design your anode to have a low voltage, and cathode has a high voltage, so the difference can be high. So that's your output voltage, and you want to maximize their capacity. So in this way, you can increase their energy density. And we also mentioned that you have electrolyte sit in between those two electrodes. And I don't know how many of you have taken thermodynamics. So when we're talking about thermodynamics, we also are looking at the energy alignment between your electrode and electrolyte. So most of the time for the battery system, especially for lithium-ion batteries, your electrolyte is sitting outside of the the thermodynamic stability window. That means you will have the electrolyte reduced at the anode side and oxidize at the cathode side. So they form extra layers, which we call at the anode side, we call the solid electrolyte interface. And at the cathode side is the cathode electrolyte interface. They will also affect the stability of your cathode materials, of your battery systems. And in terms of different types of the electrode, there's the three major types. So the insertion or intercalation is a type I just mentioned, such as lithium cobalt oxide or graphite. They are insertion or intercalation type. And you can form also anode type, like tin and silicon, which are the all very popular anode materials. all the conversion types, they undergo the conversion reactions such as metal oxide or metal sulfide. And there's a huge demand in terms of the battery, especially for, so I just use the lithium-ion battery as a case to show. Like you see, like if there's a higher demand, this is a kind of a different scenario, meaning that if we have a large demand, you might have the shortage of the lithium raw materials or resources. So I think that's probably more relevant to this class. And when we talk about the critical minerals, and it's not very clear here. So we show like there's several like minerals that's critical to lithium-ion battery technologies, like lithium, cobalt, nickel, and manganese. And if you're going to look at, this is a kind of a life cycle showing for the batteries for electric vehicles, but for other applications, it's similar. So you go from the raw materials extraction, and so that's related to the mining, and then you have the materials processing, so you need to process them, and then manufacture them into the battery cells or battery packs. And then you have the cell, you have also cell manufacturing, and then you make the module and pack for the battery for example, electric vehicles. And then you use them, and eventually you can also recycle them to make them into those different stages. And so I think this map is quite interesting for you to observe compared to the oil or NGs, natural gas. So you can see the kind of the mining for the oil and natural gas, they are kind of with the years of the development, they are already pretty mature and also well distributed. But if you look at the distribution in terms of mining of the raw materials for lithium-ion battery, you can see the lithium is mostly centered for Australia and South America, like Chile and Argentina, as well as in China. And if you look at the nickel is in Southeast Asia and also in Russia. So Russia has taken a big share of the mining for nickel. So we know there's a kind of the war between Russia and Ukraine. So in 2022, you see the sharp increase of the nickel's price because of these geopolitical issues with those raw materials. And if you look at this processing, you can see for the lithium processing, it's mostly in China and South America. And if you go to the manufacturing, you see the limitation is even more severe. We have a majority of this manufacturing in Asia and a little bit in Europe. We have some in US. So you can see that not a balance in terms of the, if you look at the life cycle for the, just for the lithium-ion batteries. And then if we're going to look at the, if we're going to look at the battery supply chains, right, we go from the mining of the raw materials, and then we do the processing. So this is what we call the mainstream. So the kind of the mining and extraction is upstream. So if you're going to look at where we sit in US, actually we're lacking for both the upstream and the midstream. So meaning that if we are lacking, we are kind of, how to say that, there's a gap for the US lithium battery supply chains in terms of the upstream, meaning that mining and also the processing as well as manufacturing. So this is what we're lacking in US in terms of the supply chain for lithium batteries. And we are also curious about the battery price. So I think 2 years ago when we are doing that, I'm doing a similar kind of presentation, we actually has expectation that the price is going up a little bit. But actually in reality, we see it's dropping in terms of the batteries. There's a few reasons related to this drop of the battery price. One thing is that there's a cell manufacturing overcapacity because people think we will have a large demand, especially from the electric vehicle market. So there's a lot of people jump in to kind of increase the capacity. But then what we see is you have a slowdown in electric vehicle sales growth. So that kind of contributed to this drop of the price. And also there's adoption of the lower cost lithium iron phosphate based battery, because that's more cheaper and also earth abundant. You use the iron based one. And the other thing we see is even though we see kind of slowdown for the electric vehicle sales growth, but we also see a steady increase in terms of the stationary storage market. So there's also competition of different battery technologies in terms of the price. And this, I think what is interesting is we see this kind of a fluctuation of the price for the raw material for lithium batteries. So if you look at the lithium, right, you see like in 2022 and 2023, we see a spike, and now it's dropping. That's also probably contributed to the decrease of the battery price. And we also see the for cobalt, we see the up and down, up and down. And for nickel, like I mentioned, when the war between Russia and Ukraine starts, you see the spike. So this is saying that the cost for the battery material is not immune to what happened globally, right? So there are influence in terms of the geopolitical factors. And if we, so this is one example, right? So I don't know if you follow the news a few years ago, there's supposed to be a cobalt mine at Salmon, right? Is that a Salmon, right? Peter, yeah. So they already have this ribbon cutting, and then it just abruptly halt. That's due to, you see, there's a drop of the cobalt price, and then the people want to see there's no profit they can make. They just stop it because the mining is very expensive. It has a lot of costs associated with that. And there's also kind of a projection of this lithium-ion battery technology. This one is based on the minerals, right? So you see, if you have this cobalt, and you see the range, right? You see, it has a big range to fluctuate. So it's a little bit unpredictable in terms of the cobalt price. And then for the nickel, it's kind of stabilized, and the manganese also has some changes too. And if we consider the current leading technology in lithium-ion battery, which is an NMC-based one, compared to a lithium-ion phosphate, you also see the fluctuation in terms of their price. So this one also comes down to that we need to secure the access to the raw and refined minerals. And meantime, we probably want to discover alternatives, right? So you don't have so much constraint in terms of how you can access to those raw materials, and as well as a cost associated with it. So if you look at the current technology, lithium, cobalt, nickel are all the critical minerals for this technology. And if we can develop alternative chemistry that we do not, you probably will still depend on lithium, but maybe you can find an alternative to the nickel and cobalt. And for example, this lithium iron phosphate, that's a very popular technology right now for the low cost. And if we're going to look at the lithium-ion battery material supplies, so those are all those kind of critical materials for this technology. We see as I mentioned earlier, lithium is mostly centered on Australia, Argentina, and Chile. And for the graphite, which is used as anode material for lithium batteries, a majority is in China. And for nickel, I think one mentioned is Russia and also the Southeast Asia. And for the manganese, it's South Africa and Australia. And the cobalt is a lot in the Democratic Republic of Congo, right? So you see, actually US, we don't have much of the share of either critical materials. So that's also the challenges too. And if you look at our current challenges, especially for the supply chains in US, you will see the lithium batteries, you see in US, and the U.S. company is actually a decade behind of the industrial sector, especially in terms of the mining, processing, and manufacturing for the technology. So we need to kind of improve on how we can get more access to the both raw and refined materials. And I think that's it. And in terms of why we need cobalt in the cathode materials, like I mentioned, the cathode material that Dr. Goodenough developed is based on cobalt, right? Lithium cobalt oxide. And the current technology is they're trying to dope the lithium cobalt oxide with other transition metal like nickel and manganese. So they have their different roles, right? So if I have increase the cobalt content, I can improve the cycling stability of this battery. And if I increase the nickel content, I can increase their capacity. And if you increase the manganese content, you can increase their thermal stability. So there's a role for different metals. But if you see like if I have a low cobalt content, actually the stability is not that well. So you need to find a balance in terms of low or free cobalt, like oxide cathode materials. And this one, I probably already mentioned that you will mostly see the general trend is we'll have more demand for the energy storage systems. And also we will see a large of demand of those critical minerals like nickel and cobalt that's related to the lithium batteries and also graphite. And there's a different scenarios, like I mentioned, if we keep seeing this steady demand for the lithium batteries, eventually we might see some gap in terms of the supplies and demand. This one shows a projected annual mineral demand under different scenarios. So this one is under the one specific scenario. So we can see like you will still have the projection is to 2050. Then you will have this graphite still in huge demand, and nickel and copper, which used as a current collector for the anode material for lithium batteries. And also in terms of the percentage, you can see lithium, graphite, and cobalt, they all have a huge percentage in terms of the demand. So we do have a lot of challenges in terms of how to get those materials for lithium batteries. So one of the consideration is you probably want to see which element is more abundant, right? So if we look at this is a kind of interesting map. So you see like those yellow color means limited availability, right? So we have lithium is limited availability. And let's look at cobalt. Cobalt in orange is like a rising threat. So it's even worse, right? And if nickel is also limited availability. Okay, so if we want to use a more available element by looking at this periodical table, which element you think will be useful if you were to design a new battery system? Hydrogen? Yeah, hydrogen might be a good one. So there's also work like, especially fuel cells, right? You can use the hydrogen as a fuel, and you can also do the energy conversion. Yeah, sodium. Sodium is very good. Sodium is very abundant, and then it's evenly distributed globally. Sodium is a very good choice. Anything else? Oxygen? Oxygen is a lot, right? So oxygen, actually people are thinking about using oxygen. So lithium air battery using oxygen, but oxygen's challenge is also similar as what you see in the fuel cell field is oxygen reduction is a kinetic limited reactions. So it's very slow. So there's also a lot of issues associated with oxygen redox. Due to this irreversibility, but that's a good thought. Anything else? Yeah, silicon is also a consideration. So because like we said, graphite is a kind of the mainstream for the anode materials. But graphite, the capacity of graphite is 375 milliamp hour per gram. It's not that big. So people are trying to use the silicon because silicon has over 4,000 milliamp hour per gram. And it's also abundant and cheap, right? Because we use that a lot for semiconductor industry. So people are trying to mix silicon with graphite or carbon for the new generation of the anode materials. Very good. I think you have all like a right kind of a perspective on the materials too. The other one you want to think is iron. Iron is also a good candidate for you to think to utilize for the battery technology. Okay. Okay, and then for the people who are still like interested with cobalt, there's also like other issues to think about because cobalt is mostly made by the Republic. Let me see. People are using the most of the. Let me see, it's where the cobalt is. Oh yeah. So the cobalt is mostly kind of mined in the Democratic of Republic of Congo. So they have like abuse of child labor. So there's also issues related with kind of use of cobalt like mine at the DRC. So then one of the kind of R&D in the field is to try to see if we can have materials without cobalt or low cobalt. And if you recall the figure I showed earlier, is cobalt is increasing the stability, right? So if you don't have cobalt, you might lose the stability. Then that might be also a potential issues, right? So those are the kind of current effort in the field is trying to develop a different chemistry without cobalt. So you see this this light blue is a baseline for the commercial one. So this is 622, so means that a cobalt is 20%. And if you decrease the cobalt, you can see you can do 5%. Actually, it's promising. You can still develop the chemistry which is comparable to the commercial one. So I think that there's a promise to develop a cobalt-free battery chemistry that can provide a similar performance. And the other thing is you can also recycle your materials and then retrieve those cobalt to make it into a new battery system. Then you can reuse it, right? So this is a kind of benefit to recycle the lithium batteries. And this one to show like you can have the cobalt from the spent lithium batteries. And there's a kind of, if you want to, there's also challenge for lithium-ion battery compared to the lead acid battery that you use in your combustion engine fueled cars, right? Because it's very easy for us to recycle the lead acid battery, and you can almost recycle almost 100% of all the materials used in your lead acid battery. But that's not the case for the lithium battery, because if you look at the make of the lithium battery, it's more complex. And so it's much more difficult to extract the materials from the used batteries. So that adds some kind of challenge technically. So there's a different ways people can recycle the batteries. You can use either the kind of direct recycling, or you can just use a pyrometallurgy, and you just smelt it and then make it into a slag, or you can do the hydrometallurgy using some chemical treatment to leach the element and then to retrieve that. But the other things like some of you mentioned, like consider sodium, right? So that means that you can also consider other battery technology beyond the lithium. So this is a kind of a current effort, right? One thing is like the sodium-ion batteries, and you can also have magnesium battery or sulfur-based battery. And so there's a lot of effort trying to develop a different chemistry. And we see here you have also lithium air battery, like some of you mentioned about the consider oxygen. And so one of the kind of the battery system, especially in my group, we are interested is develop the sodium-ion battery technology. So as we mentioned that sodium is abundant, and if you look at their abundance in both the Earth's crust and in seawater, sodium is much, much more abundant than lithium. And the kind of the benefit to develop the sodium-ion batteries because they are very close along the periodical table, so they share similar chemistry, and you can have easy drop in terms of the manufacturing for lithium to like transfer it to sodium chemistry. So this is a benefit of sodium. And if you want to compare those two kind of technology, one thing is it's abundant for sodium, and you can use cheaper and low cost raw materials for sodium chemistry. And but there's also kind of limitation, right? Because the sodium is heavier and sodium has a higher electron potential. So in theory, the energy density will be smaller than lithium. But you can think about this way: we're not trying to use a sodium-ion battery to replace totally the lithium-ion battery. It's just like you can have some alternative that if you have a lot of demand, then you have other technology that can also help to support the need, right? And but there's also issues currently with sodium-ion battery is the stability. So for example, my group, we are working a lot on how to design stable cathode materials that can operate at a high voltage. And there's also some kind of challenges in terms to establish the chemistry, also the supply chain for sodium-ion batteries too. And but the benefit, like we mentioned, is if you're looking at this is the 2023 Department of Energy Critical Materials Assessment, you can see the short term and the medium term, right? So if we look at the short term, you see the cobalt is already in the red zone, right? The lithium in the yellow zone, and in the medium term, both lithium, nickel, and cobalt are in the red zone. That is a major minerals used for lithium batteries, right? So then we want to tap more into like a manganese or titanium, or that not showing iron because iron is more abundant. So those are the considerations you can think about then you have less of the dependence of the critical minerals, but they can provide a comparable performance in terms of the battery technology. So, okay, I'm going to just end in this slide. This is one of our work. We're trying to develop the layered transition metal oxide, and that you can use more earth abundant materials to give a kind of a competitive performance in terms of the sodium-ion battery chemistry. With that, thank you all. I'd happy to answer any questions.
So that was wonderful. And as always, we go into our breakout rooms, and I apologize for not having set this up in advance. So I need to somehow do this now to find and I might need some help. Ajay, if you can come help me here with compare the cobalt-free batteries, pros and cons with the current lithium batteries. Can we be totally independent on cobalt minerals for batteries? If not, why? Any solutions to current cobalt mining? What is your perspective on battery recycling? So please go ahead and start talking about this at the tables and also in the breakout rooms, and I will share. Let's now focus again. Questions for our speaker, and we will see who is going to go first. You may start here at the prompts or any other questions that you might have for Dr. Shang.
Oh, your question is we talk about the sodium-ion batteries. Have we thought about the recycling of sodium batteries? Yes, we did. But you know, like the recycling also depend on the volume that you recycle, right? So current sodium-ion batteries is still in the early stage. Like if you look at the US, we probably only have a handful of the companies that are based on sodium technology, and there are more in like Asia, like in China, they commercialize the sodium technology. I think if you produce more, then there's more need for recycling. So, but it's also good to think beforehand. And we also have a discussion with like some of the colleagues in the field. They say the reverse design, right? So with the recycling in mind, when you design your material, how it can be easily recycled, I think that will be something to think about. Yeah, very good question.
What's your opinion on sodium ion batteries? With them being compared to lithium ion, so lithium ion's been around probably a bit longer and everything, it's been had a lot more time in the research and development. Right now, I think sodium ion's at like 2/3 the energy density, roughly, give or take, lithium ion. I guess how much more meat is on the bone for sodium? Do you think it's going to catch up quickly, or do you think that it's kind of like technology and research and development so good on both, where it's kind of like they're both kind of maxed out, or will increase at the same rate?
Yeah, so your question is how maybe sodium technology to catch up with lithium, right? With the lithium, it's so maybe advanced right now. I think that's also a good question. If you look at my slide I showed earlier, right, we see this fluctuation of the cost for the raw materials fluctuate, right? That will also affect other chemistry like sodium, right? Because if lithium is so cheap, why the people want to develop other materials? Unless lithium, we are short of lithium, we cannot have any more lithium, then you thought about other alternative. So I think that's one of the things that we need to consider is looking at this cost fluctuation to see where sodium sit. Right now, sodium's big competitor is lithium iron phosphate. So when we are designing materials, we are having lithium iron phosphate technology in mind because iron-based also cheap, right? And also, but the energy-wise is similar to sodium because the lithium iron phosphate has a lower voltage compared to the cobalt oxide. Lithium cobalt oxide. And the other thing is also we need to build up this ecosystem for the supply chain. Sodium is no exception. If there's less of the demand, then there's less need to produce the materials needed for sodium, then cost will be high, right? So if it's the cost high, then the manufacturer will not want to do it because they cannot make a profit. So those are the things we need to consider, yeah. Okay, so your question is, do we have can we use, if the recycling can get enough material for the spent batteries that we don't even need to mine, right? That's a good question too. I think that also need to see how we can collect those used batteries, right? So I think you need to have also policy in place or like an infrastructure. If you think about the lead acid batteries, you can just drop your battery in any like auto stores, right? But right now we don't have that for lithium ion batteries. So I think that really depends on how you can build up the infrastructure. Then people can easily maybe kind of drop their used batteries. Then maybe I haven't done the calculation, but I still think we might still need to mine, even though we successfully recycle all the used batteries because of the demand is increasing. Okay. Dr. Muller says the current change of the political climate is how that affect our own lab research. I would say that we will see a sharp increase in terms of the materials that we're going to use for the battery. For example, the precursors, chemicals we buy, and even just right now in our lab we test the coin type cells. So we used to buy it from a Japanese company, and the price is already increased yearly. We just ordered 1,000 pairs of the 1,000 sets of the coin cell parts, and that's already I think $3,000 higher than we original order. But with this tariff thing, we just afraid it's going to double. We're thinking to order it now to save in terms of the cost. So it's definitely is going to impact the research, especially right now. I think we have a lot of competitions from around the world, Australia, Asia, like China, Korea, and even Europe, right? If we just kind of halt our research activity here, then we're going to lag behind even more. Should I talk about that? That we'll still need to see the effect, how that's going to evolve, because due to those funding changes that also limited our ability to hire new students, right? If we don't have new students to continue to the research effort, we'll also see this decrease in terms of the research activity in the future. I would say we still need to have more investment on that, right? If you don't invest, then you don't have the resources to develop, because you cannot just come from vacuum. I think it's also need to, I feel people need to make an informed decision. That means not just like us who work in the field, like everyone in the audience, right? You need to have the right understanding of our technology. Then you can, maybe if people ask you, you can support, right? Because you have the information. So it's just, I think everyone's effort to trying to let everyone knows the importance of developing those technology and what is needed, right? Because we see how those materials, those minerals is distributed globally. So we cannot isolate ourselves because you don't have all the materials. You need the support from people from other countries, right? In order to make the technology to work. So I think we still need collaborations.
Michael, what you got? I was wondering, because you're talking about the balance between sustainability, performance, and like when you come to like a problem where like there's issues of sustainability with like lithium or cobalt, how do you decide like whether you're going to pursue like an engineering alternative for the battery to try to avoid the sustainability problems, or to focus on just improving the sustainability by seeking like sustainability solutions?
Okay, so your question is how to balance between performance and sustainability, right? And how do you prioritize which one you want to kind of consider first, right? That's also really a good question. Like we mentioned about the case for sodium batteries, right? If you look at the performance wide, the energy density still will be lower than lithium, right? But if we look at sustainability, I think it's really probably going back to Dr. Muller's question is how easily you can access the materials, right? Because sodium, we can easily get it. But now if we are limited in terms of the barriers to get those critical materials, then your options probably is more sustainability in term. You can compromise some of the performance. But if you can get, that also has a kind of things to think about engineering, because if you look at the sodium case, even though the theoretical energy density is lower, but through engineering, actually you can get a comparable performance. So I think that's probably the question as for like an engineer, how you can make it more efficient and that you can get a competitive performance. Yeah.
So Claire, if I could ask, because I think this is something that Colin mentioned, but Michael's question builds on performance versus sustainability. But you mentioned in the discussion of sodium, I think at the site, the possibility of reverse
engineering. Yeah.
So that recycling was easier.
Recyclability, yeah.
How many different sort of issues sort of go into this choice? Because it feels like there are a lot.
Yeah, there are lots. So if you think about how we make the mostly the common kind of format of the electrode is a composite, right? So then you have your active material, and then you have the binders, and you have the additive, and your active materials contains multiple elements: lithium, nickel, cobalt, manganese, right? So how you can easily separate them, I think that's a kind of a design problem to think about, right? Or maybe you can have a way that can be easily separate. So when you think about the recycling, you need to separate your electrode, and also you have electrolyte, right? Some people are interested to recycle the electrolyte, how you can easily separate them. And then in terms of the making the composite, is there either way that you can separate the composite? So.
Ian.
Going to kind of the more performance side of things, like when you're looking at what kind of metrics go into determining the performance of a battery. I guess I kind of measure things because I don't really know much about the field of energy density. What are some other important factors that go into battery manufacturing, like maybe voltage regulation, like the ability for them not to be hit super hard and then be able to discharge really quickly? What are some like drawbacks and stuff that happen with sodium versus lithium ion?
Yeah, that's a good question, right? You mentioned in terms of the what is the metrics you're going to look at in terms of, for example, the voltage, right? So if you
Sorry.
summarize it again.
Yeah, just for the people so like you sort of summarize. Dr. Muller and I were worried that you started answering Ian's question.
Oh, I'm trying to summarize this.
My apologies. That's what I jumped the gun there. My bad. Sorry.
So I can repeat, right? So his question is trying to see what is the difference in terms of the metrics compare lithium-ion battery, for example, with sodium-ion batteries. Like one example is the voltage, right? So if you look at the lithium, they have a very flat and plateau. If you look at their profiles for the cycling, right? So for lithium, but for sodium, it's very different. Even if you use the analog of the layered oxide, you will see a lot of stages, or it's a sloping. So those are the issues when you're developing other chemistry, you need to consider is probably think about what's your end use, right? If your end use, you don't worry too much about a flat, stable voltage. And then you probably can use more of the sodium because it has a kind of a sloping or more multiple stages, right? But if you have, I need to have this output voltage to be consistent at 3 volt, then you need to go to the lithium batteries, lithium-ion batteries, yeah.
What about their rechargeability? So like the amount of time that each one of them take to recharge?
Yeah, so the question is about the rechargeability in terms of how fast you can charge it, right? I think if you're talking about just lithium and sodium, they all have the materials they can do the fast charging applications. So I don't see a dramatic difference between those two systems.
I'm calling on myself. So, yeah, so I guess sort of thinking really big picture. Batteries are interesting because of the mismatch between the power generation and power supply, right, in the green framework. Should we be thinking about sort of green technologies where that mismatch doesn't happen? So are there things that we could be doing which is effectively sort of power on demand? I don't know enough about the hydrogen cells, but are there sort of things like, so we like natural gas because we can turn it on and we get energy on demand. So are there ways that we could avoid the whole battery problem altogether by sort of creating some relatively green mechanism that just sort of, that has that some of the capacities of, say, the hydrocarbons, that you can combust them and you get power on demand?
So Dr. Crowley's question is, can we think about a greener technology other than lithium, other than batteries?
Yeah.
Is that the correct interpretation? Yes, I think like a clean energies, right? So like a nuclear will be one thing to consider, but there's a lot of regulation you need to consider, right? Because we do need to operate the nuclear reactor safely, right? And batteries, I think if you looking at the CO2 emissions for battery technology, actually when you are doing the materials processing, you actually still release a lot of the batteries. But I guess it's like you need to see the whole lifetime of batteries. And if you consider that, right, so it's still consider a green technology. Yeah.
Yeah.
I have another big fix up.
Yeah, so your question is currently we're more like operated through a centralized model, right? With the batteries, can we kind of change the model that we can have more contributions, like everyone, if you use, for example, renewable energy? I think that would be ideal, right? So that's what we say the smart grid, right? So if you have batteries and then if you have a kind of solar panel at your house, then you can store the energy, right? And maybe you can give back or maybe use it for the appliance in your house, right? So those are I think the battery will add the flexibility, I would say, right? Because otherwise, if you consider the grid, you still, especially for the remote area, right? You need to have the access of the grid. But if you go to a really remote area, I guess you need to have batteries, right? If you need the electricity. So I think the batteries will add the flexibilities in like where you can use and when you can use.
I guess to add on to that, I guess, do you see like a point where we have like a centralized, like you have a huge battery center, let's say out in the middle of nowhere, or do you think it's better to have it like super local? And does that kind of cut back on transmission costs as well? I believe like something like 10% of energy is lost in transmission. Local battery centralized location. Will that dramatically cut down on this thing?
Oh yeah, so you are saying like if you have the batteries in individuals house, then you can avoid this loss of the energy during transmission, right? I think that really depends on the volume, the how much you need, right? Because if you need a lot, then maybe batteries it cannot satisfy that. You still need to use a grid to get the electricity, right? But if you just use for some small appliance, I think battery will be functional to work for that purpose. Because otherwise, if you want to use like if you have high energy demand, then you also need to have a large battery pack in order to provide that energy you need, right? So you also need to have that in mind. That's the same thing like for electric vehicles, right? If you want to drive your electric vehicle for 300 miles, you might need to have a larger battery pack, right? So that's the same thing. If you you need to also think about the kind of volume constraint.
Dr. Mullen, have you got any last thoughts? I am going to cut myself off, but just remember this is how much I respect and care for you all. So please join me in thanking Dr. Zhang for his wonderful.
Thank you.